We are now going to have a next lecture, the next Laudatio. And we'll get the microphone transferred. And this next Laudatio is on the work of Manjul Bhargava by Dick Gross. You have the floor, Dick.
Thank you, Ingrid. It's a great pleasure to be able to present to you the work of Manjul Bhargava. He's, over the past 15 years, he's created a fantastic body of work that's made fundamental contributions to several areas in number theory. So among those, there are four that I'm going to discuss for you today. He generalized Gauss's famous composition law for binary quadratic forms. He counted number fields of small degree with bounded discriminant. He bounded the average rank of elliptic curves over the rational numbers, the rank of the group of rational points. And he has shown that most hyperelliptic curves of higher genus have no rational points at all. These are all extremely important contributions to the fundamental areas of the subject. But what's more important is that he's created a method. And this method combines very detailed studies of integral orbits and finding arithmetic interpretations for these integral orbits in group representations with techniques from the geometry of numbers. It's just a whole panoply of mathematics. In integral orbits, it involves algebra, arithmetic, representation theory, and the enumeration of those orbits involves new ideas in geometry and analysis. It's just beautiful work. Now, before I discuss these results of Manjul's, I want to review for you the first case where integral orbits were studied in mathematics and where the geometry of numbers was used to enumerate them. And that goes back over 200 years to the work of Lagrange and Legendre and Gauss on binary quadratic forms. Binary quadratic form is a quadratic function in two variables, x and y, with integer coefficients a, b, and c. And some definitions. Well, first, to a form, we have its discriminant, which tells you the quadratic extension where the form has its two roots. We say a form is positive definite if it only represents positive integers. No matter which integers x and y you put in, the quadratic form takes positive values. That occurs when a and c are positive and when the discriminant is negative. And in this talk, I'm only going to talk about positive definite forms. And also we say a form is primitive if the greatest common divisor of the coefficients is 1. That means that the integers that it represents are not all divisible by some number bigger than 1. So the fundamental work of Lagrange and Legendre studied the action of the group SL2. Actually, they studied the group of 2 by 2 integral matrices, which are invertible GL2, on binary quadratic forms by changing basis. This quadratic form just gives a quadratic function on a free module of rank 2 over the integers, and you can change basis and you represent the same integers. And they considered two forms equivalent. Let's say two forms are equivalent if one is taken to the other by an element in SL2. And that's the group action. And they proved, first of all, that every orbit contained a unique representative where the coefficients satisfied these inequalities. Those are called reduced forms. Another way of saying this is if you take the two roots of a reduced form, one of them lies in the fundamental domain that everyone writes for SL2Z on the upper half plane. And from this result, it follows very simply that there are only finitely many orbits with a fixed discriminant. Indeed, for a reduced form, 3 times AC is less than the absolute value of the discriminant. And that gives only a finite number of possibilities for the integers a and c, and then only a finite number of possibilities for b. So those results are due to Lagrange and Legendre, but the most important result was found by Gauss in the disquisitiones. Now, the group action preserves primitive forms, so you can restrict to the orbits which are primitive of a given discriminant. And he showed that that finite set of orbits had the structure of an abelian group under a law that he called the composition of binary forms. You could take two forms and compose them to get a third with the same discriminant. And this composition law, if you knew the orbits of the first two forms, you knew the orbits of the composed form. And that law gave a group structure on this finite set. Almost half the disquisitiones is devoted to binary quadratic forms, and the material on Gauss composition was considered the most difficult section of the disquisitiones, occupies several 20 or 30 pages. Now, nowadays we would say that this is a group action and we're classifying the integral orbits. It's an action on the symmetric square of the standard representation, that's binary quadratic forms. And we have an interpretation of Gauss's theorem of composition in that we know, following Dedekind, that the primitive orbits of the given discriminant turn out to correspond bijectively to the elements in the ideal class group of that quadratic ring of discriminant D. The ideal class group is the quotient group of the group of fractional invertible ideals by the subgroup of principal ideals. That's a much simpler definition. But if you actually want to work out the structure of that abelian group, you go back to Gauss composition because that's what works as an algorithm to calculate. Now, Gauss asked, after all this structure was determined, at the end of the disquisitiones, he asked, how large is the class number? It's a finite number. How many orbits are there of a given discriminant? And this was the kind of question Gauss loved because it was amenable to computation. And he computed for thousands and thousands of discriminants. And he convinced himself that the class number was growing at essentially the same rate as the square root of the absolute value of the discriminant. Now, he couldn't prove that, and we can't prove it effectively today. But he did prove a result that convinced him it was true on average. Namely, he stated the following result, that if you took the sum of the class numbers for absolute value discriminant less than t, it was a constant, pi over 18 times t to the 3/2 power. If you integrate a constant times x to the 1/2 power from 0 to t, you get a constant times x to the 3/2 power. And so we don't have Gauss's proof of this result. It's just a statement. But we suspect that he used the geometry of numbers to do it, because he had also worked on a famous problem he called the circle problem, which was to estimate the number of integral points inside of a circle of radius r. Since each square occupies something of area 1, your first guess would be the number of integral points inside the circle is pi r squared. Of course, that's not exact, but Gauss was able to prove that the error term was less than a constant times r, the radius. We actually suspect the error term is much less, but that's still an unsolved problem. But the simplest fundamental idea in geometry of numbers is to estimate the number of integral points in a bounded region. The first guess would be the volume of the region. Now, let's go back to his statement, and I'll give you Merton's proof. Well, first of all, the sum on the left-hand side, by the theorem of reduced forms, is just the number of points in this region in 3 space, where x, y, and z are bounded by these inequalities. That's the reduced form. And then the discriminant in absolute value is less than t. And that's a region that turns out to have finite volume. And if you're good at triple integrals, or you know how to use Mathematica, you can compute that its volume is pi over 18 times t to the 3/2 power. Now that would give an argument to show that the number of integral points was approximately that volume if this were a bounded region. But it isn't. It has cusps. Here's a projection of, here's what the region looks like for y equals 0, the area under that hyperbola. And so when you have a region with finite volume which has cusps, you have to be extra careful in using the geometry of numbers, because a priori there could be an infinite number of integral points far out in a cusp that had essentially volume 0. In this case, there aren't, and that's the final part of the argument. And all parts of this argument are going to be used by Bhargava in much more sophisticated examples than this simple representation. Well, enough of the history. Let me tell you a little bit about Manjul's work. In his thesis, he found a fantastic reformulation of Gauss composition, maybe the first progress on Gauss composition for 200 years. And he studied the action of 3 copies of the group SL2Z, acting on a representation, an integral representation of dimension 8, the tensor product of the 3 standard representations. Now, here's how he looked at it using his version of cubes. A vector in that representation, there's 8 integers, can be viewed as a labeling of a cube. And you can slice a cube 3 different ways: front, back, left, right, top, bottom. And each way you slice it gives you 2 by 2 matrices. Here they are. Here's the front, back, the right, left, top, bottom. And to a pair of 2 by 2 matrices, you can make a binary quadratic form by taking these determinants. m1x minus n1y. Take the determinant of that. That gives you a quadratic polynomial in x and y with integer coefficients. And so, from a vector in the cube, you get 3 binary quadratic forms with integer coefficients. Now, the first thing you show, which Manjul observed easily, was that these forms all have the same discriminant. All 3 of these forms have the same discriminant, and that gives a quartic polynomial in the coefficients of the cube, which is a polynomial invariant on the representation. But they're not arbitrary forms of that discriminant, because they're all made from the same 8 integers, so there must be some relation between them. He also observed that if you take the orbit of the vector under the action of the group on this representation, you get 3 different binary forms, but they're all in the same classes. So you really get from the orbit of the vector 3 different SL2Z equivalence classes of binary forms. And so 3 ideal classes for that quadratic ring. And the key relation that he noticed was that their product is 1. And in fact, that every triple of ideal classes with product 1 came from this representation. So the orbits on this representation are in bijection with triples of ideal classes, given by these 3 binary forms, with product 1. Another way of saying that is, if the product of the forms is the trivial class, and that's the class that represents the integer 1, then the 3 forms come from a cube. And this is a fantastic symmetric reformulation of Gauss composition, which simplifies all the formulas in the disquisitiones and is much more amenable to computation. Well, that was just his PhD thesis. Manjul didn't stop there. He found 14 integral representations that had a lot of similarities to Gauss composition. They don't compose anything anymore, but he could parameterize the orbits in terms of arithmetic data. For example, if you take this representation and you restrict to the diagonal SL2, this tensor product of 3 representations is no longer irreducible, but it has an irreducible piece, which is the symmetric cube. And that gives the action of SL2 on binary cubic forms of this type. What are the orbits? Well, the 3 ideals are the same. So you just get a quadratic ring and an ideal class whose cube is 1. And so this representation parameterizes quadratic rings and ideal classes of order 3 in that ring. Well, among these 14 representations, there were 3 very special ones. And they're the action of GL2 on ternary quadratic forms, the action of SL3 cross GL2 on pairs of ternary ternary quadratic forms, and the action of SL5 cross GL4 on 4 tuples of exterior 2 forms on 5 space. Now, where did they come from? Well, it turns out that all of these 14 representations, Bhargava discovered, occur inside of Chevalley groups. They occur with the action of the Levy factor on the unipotent radical of a parabolic. And these 3 occur in the exceptional groups G2, F4, and E8. And they occur in the only parabolics that are both maximal and special in the entire theory of Lie groups. And they have wonderful, wonderful properties. For example, they each have a polynomial invariant that generates all the others of degree 4, 12, and 40. notice that that's the same degree as the dimension of the representation. And they have finite stabilizers of the orbits where the discriminant is non-zero. And Manjul proves that the orbits of these three representations correspond bijectively to cubic rings, quartic rings, and quintic rings, rings which are free Z modules of rank 3, 4, and 5. And this invariant is just the discriminant of the ring. Now recall that if you have a ring which is a free Z module of rank n, you can define its discriminant by the determinant of that symmetric n by n matrix of traces. Well, this theorem was known for n equal 3. It had been proved by Delone and Fadeev. But the quartic and quintic cases were infinitely more complicated because you didn't just get a ring, you got a ring with additional data. In the quartic case, a cubic resolvent. In the quintic case, a sextic resolvent. And the algebra involved in passing from these orbits to the ring is just phenomenal work. But then, Bhargava decided to use the argument of Gauss and count these rings using the geometry of numbers. And he used this to enumerate number fields which have small degree. So to recall, for those of you who haven't studied number theory, a number field is just a field which, as an extension of the rational numbers, is a finite dimensional vector space. And that dimension is called the degree of the field. And inside of every number field, there's a natural ring of rank n, which is called the ring of integers. It consists of all the elements that satisfy integral equations over the integers. And since we can define the discriminant of a ring of rank m, we can define now the discriminant of a number field by taking the discriminant of its ring of integers. And those are the two fundamental invariants of a number field, the degree and the discriminant. They're the first thing you define in a course on number theory. But we know very little about them. For example, we suspect that if you take all the number fields of a fixed degree and you bound their discriminant by t, that the number of such fields grows like a constant, depending on n, times t. That's known for quadratic fields, where it's easy, and it's known for cubic fields. That was proved by Davenport and Heilbronn. But Bhargava proves it for all fields of degree less than or equal to 5, and his work leads to a guess of what the constant is in general. And the constant is always given by a product of local terms. So for example, for degree 5, the constant is this. Now, how does he prove this wonderful result? Well, he does the same as Gauss did. He takes the representations he used to parameterize cubic and quartic and quintic rings, and in each case, he constructs a fundamental domain in the real representation. That's like the reduced forms. And then he calculates the volume of that region. If you bound the height by t, that was like Gauss's computation of the volume of that region. And of course, the region has cusps, much more complicated than the case of binary quadratic forms. So he has to estimate the number of integral points in a cusp to show that it doesn't screw up the volume estimate. And finally, that's just counting the rings of rank n. He has to introduce a sieve to count the rings which are maximal and are integral domains. It's a fantastic generalization of Gauss's work. But all of those representations, all of the representations he found that generalized Gauss composition, I should say Gauss composition comes from the exceptional group of type D4, where the parabolic subgroup has triality operators, and that's what gives the three different ideal classes. All of these representations have the property that their invariant theory is very simple. There's a single polynomial that generates all the ring of invariants. But then he took a look at the most famous representation that has two polynomial invariants, and that's related to elliptic curves. Now, Manjul is going to talk about this in his talk at the Congress, so I can be brief. In any case, he'll do it much better than I would. So I urge you very strongly to go to his talk on Friday at 11:30. If you haven't been to one of his talks, you're in for a real treat. Now, the simplest representation, which has two independent invariants, is the action of SL2 on binary quartic forms, or what we would say is the symmetric fourth power. There are two invariants which are independent. One is of degree 2, one is of degree 3. And the polynomials in A and B generate all the invariants. And there's a famous polynomial of degree 6 called the discriminant, which is the discriminant of the quartic form, whose non-vanishing determines the orbits that we would now say are stable in the sense of geometric invariant theory, subject discovered or developed by David Mumford. And that means that the orbits are closed and they have finite stabilizers. In this case, the stabilizer is order 1, 2, or 4. Now, associated to each stable orbit, you get an elliptic curve defined by this equation, because the discriminant being non-zero says that that cubic equation has 3 distinct roots. And when you have an elliptic curve over the rationals, you may want to know what are the rational solutions of that equation. And what's wonderful about elliptic curves is that the space of rational solutions forms an abelian group. There's a group law because if you take any line through 2 points on the curve, it meets the curve in a 3rd point, which isn't, and the sum of those 3 points is 0 in the group law. So the sum point is what you obtain by projecting across the x-axis. And this abelian group has a beautiful structure. Mordell proved about 100 years ago that it was finitely generated. So it has a certain number of independent generators and a finite torsion group. The torsion group is known. That was work of my colleague Barry Mazur. It proved that it had order less than or equal to 16. But we know very little about the number of independent generators, which we call the rank. When the rank is 0, that means it's a finite number of solutions. When the rank is positive, an infinite number. So is the rank bounded, for example, if we look at all elliptic curves over the rational numbers? The answer is that no one knows. There are people who believe it's bounded. There are people who believe it's unbounded. The current record is held by my colleague Noam Elkies, who found an amazing curve of rank 28. And another question we might ask is, what's the rank on average? If we looked over all elliptic curves and averaged by letting the coefficients a and b get larger and larger as integers. And people had guessed that perhaps the rank on average was a half. That in the sense of proportion, 50% of curves should have rank 0 and 50% should have rank 1. That doesn't mean that none of the curves have rank 2 or more, just that they're very sparse. Well, as Manjul will show you in his talk, the computational data didn't really support that, but his results do. And he proved a wonderful, wonderful theorem with his student Arul Shankar, who's also at this Congress, by studying the orbits on this representation of binary quartics and also ternary cubics. And they proved that the average rank is less than 1. Now, before this result, no one could even prove that the average rank was finite. Perhaps as you let A and B get large, the rank kept getting larger and larger. But this is the first piece of evidence that perhaps the average rank is a half. And they prove stronger than this, namely a positive proportion have rank 0, so have only finitely many points, and a positive proportion have rank 1, so have an infinite number of points. And they also prove that at least 80% have rank either 0 or 1. I should say that recently, and this I believe will also be covered in Bhargava's talk, they've compared these results to results that have been known on the conjecture of Birch and Swinnerton and Dyer, which predicts the rank in terms of the number of points taken modulo primes. And they now have Manjul has a result with Chris Skinner and Wei Zhang that the conjecture of Birch and Swinnerton and Dyer is true for 66% of elliptic curves over the rationals. This is just unimaginable work. No one even thought in these directions. And I'll finally finish with his work on rational points on hyperelliptic curves. So this just to show you that the theory isn't limited to genus 1. A hyperelliptic curve is given by an equation y squared is a polynomial in x, where the polynomial has non-zero discriminant. And the degree of that polynomial I've made even, that defines what's called the genus of the curve. And Faltings had proved in '83 that if the genus was at least 2, the number of rational solutions of this equation was finite. There are only finitely many values of x where when you put them in that polynomial, you got a square. That's the Mordell conjecture for curves of genus at least 2, and that was awarded a Fields Medal at the Congress in 1986. Well, Bhargava showed much more. He showed that a majority of these equations have no solutions whatsoever. Namely, for no value of x when you put it in this polynomial, is it going to be a square. And not only is it a majority, meaning more than 50%, but it tends to 100% very quickly. Namely, once you get the genus to at least 10, at least 99% of hyperelliptic curves have no rational points at all. which teaches us that if we're going to work with the arithmetic of curves, we better learn how to work with curves that have no rational points. So it's been a real pleasure to try to give you some idea of Manjul's work. I want to end with a quote from another number theorist who wrote me the sense about his work, the sense of a new field opening up before one's eyes with an elegance and clarity that remind one of one's first encounters with classical mathematics is unique and sometimes breathtaking. That comes from Andrew Wiles, who was Manjul's thesis advisor at Princeton. I think all of us feel the same way. As I say, it's an honor to speak on his work and a pleasure to speak in front of you. Thank you.
Thank you so much, Dick.